Welcome back to the second part of the APEC Econ Chemistry Chapter 6 homework review. Let's pick up with problem number 15. You are asked to consider in problem number 15 a line that's on the Lyman part of the hydrogen spectral series, and that means n low equals 1. You're told that the wavelength is 97.23 nanometers and asked to figure out what the high energy level and high is from this. So given that wavelength, you can find the frequency, which is a little bit easier to deal with for the next part here. So you do a little algebraic rearrange it with c equals lambda nu and find that the frequency is 3.083 times 10 to the 15th hertz, or per seconds. You can take that frequency and then plug into this variation of the Rydberg equation, where a constant over Planck's constant, the Rydberg constant over Planck's constant, is equal to 1 over n low squared minus 1 over n high squared. Plug in your values for the Rydberg constant, the Planck's constant, and your constant, or your value of 1 for n low, since you know it's part of n low based on the original information given, and you can kind of simplify this and find out that the only thing you don't know is n high squared. So you know that the frequency, this from the previous slide, 3.083 times 10 to the 15th per second, is right here, frequency, is equal to the simplification on the right side of this equation here, where only 1 over n high squared is unknown. You can divide both sides by 3.329 times 10 to the 15th per second and find that there is a unitless value that now equals 1 minus 1 over n high squared. If you subtract the 1 from both sides, you'll find that both sides are equal to a negative number that goes away, and you can actually solve out algebraically that n high eventually is equal to 4. Let's take a look at problem 17. In this particular problem, you're asked to consider quantum numbers. You're asked to figure out what are the possible m sub l, the orbital quantum numbers, for, in this case part A, a d sublevel. So you can refer to the information present in table 6.3 from your textbook and find out that a d sublevel should have values of -2, -1, 0, 1, and +2 possible for a given d sublevel. So an orbital could be coded as -1, -2, +2, -1, or 0. An s sublevel will have to have an orbital quantum number of 0. And if you're considering all the sublevels that are present on n equals 2, when n equals 2, it's possible for, from the principal quantum number, it's possible for the second quantum number L to be 0 or 1, associating with an s or a p orbital. If L is 0, then n sub L must also be 0, considering like an s orbital. And if L is 1, it's possible for m sub L, your orbital quantum number, to be -1, 0, or +1. Let's take a look at problem number 21. Problem 21 asks you to consider, again, orbitals, and you're trying to figure out what orbital is designated by the following quantum numbers that are given, and we're looking to try to pick out S, P, D, F, and what energy level these orbitals exist on. So if n equals 3, we're dealing on the third energy level. If L equals 2, we're dealing with a d sublevel. And if m sub L is -1, it's one of the orbitals within that d sublevel. For part B, if n equals 6, then L is equal to 3, and m sub L is equal to 2, we're on energy level 6. When L is equal to 3, we're considering an F sublevel, and it's one of the orbitals within that F sublevel if m sub L equals 2. If n equals 4, again, we're dealing on the fourth energy level. N equals 4 over here. When L equals 3, we're still dealing with an F sublevel. We're dealing with a different orbital within a different sublevel, because m sub L equals 3, so it's another different orbital within the fourth energy level.